Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Network Address Translation, or NAT, is one of the most important technologies for enabling communication between internal devices using private IP addresses and the public internet. It serves as a translator between address spaces that are not inherently compatible, especially between RFC 1918 private IPs and globally routable public IPs. NAT allows multiple internal devices to share a single public IP, conserving address space and simplifying routing. At the same time, it offers a layer of abstraction that hides internal network structures from external observers, adding privacy and making networks easier to scale. The Network Plus exam covers NAT in multiple contexts, particularly when discussing addressing, routing, firewalls, and internet-facing devices. You may encounter questions that require identifying when NAT is necessary, choosing the correct type of NAT for a scenario, or interpreting the effects of NAT on packet behavior. You might also see NAT as part of a diagram showing internet traffic flow, where identifying how and where translation occurs is critical to understanding the network design. To succeed on the exam and in practice, you need to understand both the technical function and the strategic use of NAT. At its core, NAT works by modifying packet headers as they pass between networks. Specifically, NAT replaces the source IP address of outbound packets, typically private addresses not routable on the public internet, with a public IP address assigned to the router or firewall. When a response returns from the destination host on the internet, NAT uses its translation table to reverse the process, directing the response to the correct internal device. This translation allows private devices to access the internet seamlessly, despite the fact that their original IP addresses would otherwise be rejected by external routers. NAT typically operates at the network edge, usually on a router or firewall that connects the local area network LAN to the wide area network WAN. As outbound packets leave the LAN, the NAT device inspects the source address and modifies it, recording the original internal IP and port in a temporary table. This way, when return traffic comes back, the device knows exactly where to send it. The NAT device also modifies the checksum in the IP header to maintain packet integrity. This process is continuous and dynamic, allowing for thousands of concurrent translations in enterprise networks. Static NAT is the most straightforward form of address translation. It maps one internal IP address to one public IP address in a permanent one-to-one relationship. This configuration is useful for situations where an internal device must be accessible from the public internet, such as a mail server, VPN concentrator, or web server. With static NAT, the external IP address always corresponds to the same internal IP, ensuring consistent access. While this provides predictability, it does not conserve public IPs, making it impractical for environments with many internal hosts needing external access. Dynamic NAT is similar to static NAT but adds flexibility by using a pool of public IP addresses rather than assigning them one-to-one. When an internal device initiates a connection, the NAT device selects an available IP from the pool and temporarily assigns it for the session. When the session ends, that IP returns to the pool for use by another device. This method conserves public IPs better than static NAT, but it still requires a sufficient number of public addresses to accommodate concurrent sessions. If the pool is exhausted, new outbound connections are temporarily blocked. The most widely used form of NAT is port address translation, or PAT. Also known as NAT overload, PAT enables many devices to share a single public IP address by assigning unique port numbers to each session. When a device initiates a connection, the NAT device translates the source IP and assigns a unique source port for the session. It then records this in a translation table. When the response comes back, the NAT device uses the port number to determine which internal device should receive the traffic. PAT is what allows entire households or companies to operate online through one ISP-assigned IP address. To make PAT work effectively, the NAT device must maintain a detailed translation table. This table includes the internal IP address and port, the assigned public IP and port, and the destination IP and port. Each entry remains active only as long as the session is open. If a session becomes inactive, the entry is removed after a timeout period. This dynamic tracking is what enables simultaneous connections from dozens or hundreds of devices using a single IP. Because each session has a unique port mapping, the NAT device can correctly route all responses back to the initiating device. Inbound traffic through NAT introduces some challenges. By default, NAT blocks unsolicited inbound packets because it has no entry in its table indicating where the packet should go. To allow external systems to initiate connections to internal devices, port forwarding must be configured. This technique creates static rules, mapping an external port to a specific internal IP and port. For example, incoming requests on port 80 could be forwarded to an internal web server at 192.168.1.1. This exception allows services like web hosting or remote access to function behind NAT. NAT offers several benefits for enterprise networks beyond address conservation. It increases internal security by making internal IP addresses invisible to the public internet. It allows organizations to use any private IP ranges internally, avoiding conflicts with other organizations. NAT also simplifies IP address management during mergers or acquisitions, as internal networks can remain intact while connecting to external services through a single translated gateway. In many enterprise environments, NAT is tightly integrated with firewalls, enabling policy enforcement and traffic control at the edge of the network. Private IP addresses, defined by RFC 1918, are most often paired with NAT. These addresses are not routable over the public internet, so any communication with external resources must pass through a NAT device. The most common application is a router or firewall that sits between the LAN and the internet, translating outbound requests and managing inbound traffic through port forwarding. Without NAT, internal devices using private IPs would not be able to access web services, cloud platforms, or external servers. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. NAT is often implemented alongside firewall systems, especially in edge devices that connect a local network to the internet. This integration allows address translation and traffic filtering to occur at the same inspection point. For example, a firewall can perform NAT on outbound traffic while simultaneously enforcing security rules about which internal devices are permitted to initiate connections or what destinations are allowed. And this combination streamlines network design, enabling centralized control over both address management and access permissions, while also supporting logging and monitoring for security audits. Despite its many advantages, NAT is not without limitations. Certain applications, especially those requiring peer-to-peer connectivity, may struggle to function properly behind NAT. This includes some VoIP systems, video conferencing platforms, and multiplayer games. These applications rely on external devices initiating direct connections back to a host behind NAT, which may be blocked unless port forwarding or NAT traversal is implemented. Additionally, some VPN protocols can be disrupted by NAT unless special configurations such as NAT-T, NAT traversal, are enabled. Understanding these limitations is key when troubleshooting connectivity issues or planning services that require external access. To overcome NAT's limitations in specific scenarios, a variety of NAT traversal techniques have been developed. STUN, Session Traversal Utilities for NAT, helps devices discover their public IP address and the type of NAT they are behind. It is commonly used in VoIP and real-time communication services to allow internal devices to receive calls from the outside. Turnaround using relays around NAT builds on STUN by providing a relay server through which traffic can be routed if a direct connection cannot be established. These techniques are embedded in many modern communication applications to ensure reliable operation across networks using NAT. From a diagnostic and security standpoint, routers performing NAT must keep temporary logs of translation entries. These NAT tables are crucial for tracking which internal devices are communicating with which external systems at any given time. The entries include source and destination addresses and ports, and they are stored for the duration of the session. These logs are useful for auditing, troubleshooting connection failures, or tracing suspicious activity. However, NAT tables have limits in terms of the number of concurrent sessions they can track, and timeouts must be managed carefully to avoid prematurely dropping active sessions. NAT also interacts with DNS in ways that can affect network design and troubleshooting. When a public service is hosted behind NAT, its public IP address is what is registered with DNS. External users resolve that address and reach the service through port forwarding or static NAT. Internally, however, the service may reside on a private IP. In such cases, split horizon DNS may be implemented, where internal and external DNS servers provide different records for the same domain name. This ensures that users inside the network connect directly, while users outside are directed through NAT. In IPv6 environments, the role of NAT is significantly reduced. The vast address space provided by 128-bit IPv6 addresses eliminates the need for address conservation, making NAT unnecessary in most scenarios. IPv6 enables each device to have a globally unique address, allowing direct communication without translation. NAT66, a version of NAT for IPv6, exists, but is rarely used and generally discouraged. Instead, network segmentation and access control are handled through routing policies, firewall rules, and address scopes, rather than through address translation. Despite common assumptions, NAT itself does not provide true security. While it does obscure internal IP addresses and prevent unsolicited inbound traffic by default, it does not inspect packets or apply filtering rules unless combined with a firewall. Many mistakenly believe NAT is a substitute for security controls, but in reality, it must be paired with access control lists, intrusion prevention systems, and firewall rules to offer true protection. NAT's behavior may contribute to a defense-in-depth strategy, but it is not a standalone security mechanism. On the Network Plus exam, you'll be expected to identify NAT's function in both textual and diagram-based scenarios. Questions may describe a network topology where internal devices use private IPs and require internet access. You might be asked which type of NAT should be used or how a web server behind NAT can be reached externally. You'll also need to recognize behaviors associated with static NAT, dynamic NAT, and PAT, and understand how session tables operate in a NAT device. Mastering these concepts prepares you to work effectively with routers, firewalls, and enterprise network edge configurations. Understanding NAT behavior is also important when diagnosing connectivity problems. If internal users can access the internet but cannot host a server that is reachable externally, the likely issue is a missing port forwarding rule. If a voice or video application connects but has no audio or video stream, NAT traversal or port blocking may be the culprit. Recognizing these patterns allows network professionals to respond quickly, improving reliability and user experience. In conclusion, NAT plays a pivotal role in how modern IPv4 networks function. It allows multiple internal devices to share a single public IP, enabling efficient use of address space, and providing a basic layer of obfuscation from external entities. Through static NAT, dynamic NAT, and PAT, it supports everything from internal web browsing to externally hosted services. While it has limitations, particularly with peer-to-peer and inbound traffic, these can be managed through techniques like port forwarding and traversal protocols. On both the Network Plus exam and in real-world networking, understanding NAT is essential for building scalable, secure, and functional internet-connected networks. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, Make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.